All right, time to go teach. Hello and welcome to this next episode of Tutors in the unit of Biochemistry, where we are looking at bonding inequity. Not every bond that is made by the elements that we talk about are exactly the same. And so we're going to be looking at today and how they're different. So let's get started. First off, we have to identify specific rules. There are specific rules for how elements or different particles are going to interact with each other. And you need to understand them because they are going to be a reoccurring theme throughout this course. Next, also describe polarity and how that will affect molecules. Again, polarity is going to be a very important concept that we will revisit over and over again throughout this course. And so, it's really, really important for you to understand it now. And lastly, calculate if a bond is polar or not. So we're going to look at and define what polarity is, and then you should be able to calculate whether or not a bond is polar. Let's move on. First off, key themes. The first key theme is that opposites attract. So if you have a positive charge and a negative charge, they are going to want to come together. That is important for us to understand. Next is that likes, well, they repel. So if you have two molecules or two particles with the exact same charge, they are going to push away from each other. They do not want to be close together. So remember, likes, they push away, and opposites, they attract and they come together. Particles with no charge, they don't interact with charged particles. An example that is similar to this is like if I put a magnet next to a piece of paper. The magnet is not going to stick to that piece of paper because it has no magnetic properties. Well, charged particles, they're like magnetic in a sense. Okay? They interact with other charged particles, just like magnets interact with other magnetic things. But if something is uncharged, well, the charged particle doesn't interact with it at all, just like how a magnet will not interact with something that's not magnetic. So that's sort of a way to understand it. They're not exactly the same. Charge doesn't mean it's magnetic, but just like how a magnet doesn't interact with something that's not magnetic, a charged particle will not interact with an uncharged particle. And not all of these interactions, not all bonds are equal. They are based upon the properties, specific properties of the element. And we're going to look at one specific property that's going to determine how an element interacts with its bonding. And that's what's going to cause polarity. Polarity simply is the property of having poles or unequal areas. In anatomy, we actually would even look at ourselves as having polarity because we have unequal areas. So it's just a very simple term to explain that we have unequal areas. For molecules, it's based upon charge. Does the molecule overall have a slight positive or negative area? And by the way, if it has a slight positive area, it will also have a slight negative area if it is a neutral molecule. Okay? So that is that. It's based upon the charge. Slight positive, slight negative, something on those lines. So remember, atoms are neutral overall. They have an equal number of protons and electrons. They are an equal amount of positives and negatives. So they are completely 100% neutral. But if we were able to shift the electron cloud just slightly, what you would see is that there's more positive over here and there's more negative over here. It's not an equal amount overall. And so we end up with a partial negative area and a partial positive area. And yes, that little symbol right there, that's a sigma. It means partial. So if for some reason the electron cloud gets distorted a little bit, we can end up with a slight positive and a slight negative area, thus creating polarity. Now, this doesn't occur in isolation. No atom is going to have its electron cloud slightly shift off kilter because of nothing. It's going to happen because of an interaction with another element. That is what is going to cause that electron cloud to shift in a specific direction. And that's going to be based upon a concept called electronegativity. Electronegativity, put simply, is the amount of force that one element's nucleus can have on another element's electron cloud. So when two elements bond, if this element has a very strong electronegativity, and this element has a very weak electronegativity, this element will pull the electron cloud of this other element closer to itself. That means that the negative area is going to be more over here, and this area would be slightly positive, right? Because the electrons have shifted. Now, the periodic table is arranged in a really cool way where we can actually look at a trend upon the periodic table with electron negativities. Here's how it works out. As we go down the periodic table, the electronegativity decreases. So the electronegativity is going to get smaller and 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 smaller as we go down. And as we go across the period, it increases. So the electronegativity increases as we go across the periodic table. And that means if we put those two things together, the electronegativity increases as we go up and as we go across the period. That means that the element with the highest electronegativity is all the way over here. It's fluorine. Now, it stops at fluorine because the next column, these are the noble gases, and they don't bond. And since they don't bond, they don't have an electronegativity because, again, the electronegativity is based upon how an element pulls on another element's electrons that it's bonded to. And since noble gases don't bond, well, that means they can't have an electronegativity. Okay? So, again, we increase in this way. And our scale is only from 4 to 0.7, which is down here. Here are the electronegativities for the 4 elements that we really care about. Hydrogen having an electronegativity of 2.1. Carbon having an electronegativity of 2.5, nitrogen having an electronegativity of 3.0, and oxygen having an electronegativity of 3.5. Oxygen is actually the second most electronegative element out there. So it has a very strong pull for electrons toward itself. It likes other elements' electrons. And what that means is that oxygen, well, it will pull strongly on another element's electrons, stronger than nitrogen will, and nitrogen will pull stronger than carbon will, and carbon will pull on those electrons stronger than hydrogen will. And the way we calculate a bond with this is we just calculate the difference between the electronegativities of the two elements. So if we take our elements and we make a little grid, obviously, an element bonding with itself, there is no difference in electronegativities, so there would be no difference in polarity, right? Because each hydrogen atom, it would have the exact same electronegativity as every other hydrogen atom. So the difference between the two would be 0. Carbon to carbon, 0. Nitrogen to nitrogen, 0. And oxygen to oxygen would be 0. There is 0 difference in the electronegativity of one element bonding with the exact same element. But what about the other ones? So we have hydrogen to carbon is 0.4, nitrogen to hydrogen is 0.9, oxygen to hydrogen is 1.4, carbon to oxygen is 1, carbon to nitrogen is 0.5, nitrogen to oxygen is 0.5, and that is going to be important for us as we progress and we think about what makes a polar bond. And what's important here is that at some point in time, chemists had to come up with a category to say where the cutoff was on what makes a polar bond and what doesn't make a polar bond. And that value is 0.4. Anything 0.4 or less is nonpolar. Anything greater than 0.4 is polar. So from that, we can see here that obviously the zeros are nonpolar, and the 0.4 is also nonpolar. So these are the interactions that are nonpolar. And I want you to really look at this closely and see that it's just the carbon to the hydrogen. That's the only bond that's going to be considered nonpolar. So these bonds, they are all polar bonds. And that means that the molecules that these elements form when they're bonding in these arrangements, there's going to be a slight negative area and there's going to be a slight positive area. And that means that that slight negative area, it's going to repel other slight negatives. And that slight positive area is going to attract slight negatives to it. Because remember, opposites attract, likes repel. So that's going to make for very interesting interactions, which, by the way, that's how you and I exist. That's how we're alive. If these interactions didn't happen, we wouldn't be here. So, in summary of all that, specific principles, they're going to guide how these particles interact. Likes, they are going to repel. Opposites, they're going to attract. Some elements are able to pull on electrons stronger than other elements. Those interactions are going to be crucial for how the molecules are going to interact. Next, molecular polarity. Well, it's due to the electronegativity. If elements all had the same exact electronegativity, there would be no polarity. There would be no slight positive and slight negative. There would be just pure neutral all over the place. But that electron cloud, it can get shifted a little bit, and that's going to mean that we're going to have some polarity. That means we're going to have a little bit of charge here and there, and those are going to mean that we have some really cool interactions. And lastly, the bonds between hydrogen, carbon, nitrogen, and oxygen, they depend on which other element they're bonding with. It's not oxygen always forms a polar bond. It doesn't. Oxygen, if it bonds to oxygen, forms a nonpolar bond. But if oxygen forms a bond with either carbon or hydrogen or nitrogen, then it forms a polar bond. So it's important what elements are interacting and what the difference in their electronegativities are. That's going to determine how they interact as molecules. On that note, be awesome, stay awesome.